welcome again from my side. I would like to welcome our first speaker, Randall. Randall finished his PhD from Rice University in 2020, I believe, and joined the group of Jan LeCoultre at Meta in 2021 as a postdoc. And besides that, he has also been at Citadel to work on highly noisy and non-stationary financial time series and to provide solutions for prediction and representation learning. Among other things, Randall is the author of a cookbook on self-supervised learning. So, we thought who would be a better guy to introduce self-supervised learning than the person who wrote a cookbook on it.
Thanks. First, thank you for the invitation. Very happy to be here and to speak about self-supervised learning. And so just a couple of things before going into the slides. So the first thing is that I'm happy to say that I just joined Brown as a faculty. So in case you have questions about collaboration, anything related to academic related topics, I'm happy to also speak about that later on. And another thing, as Nico said, I don't have to rush through my slides. So whenever there is a question, just feel free to interrupt me. You can either raise your hand or if I don't see you, just, yell my name, whatever. The goal is that everyone can follow each slide and we are all moving through them together. The goal is for you to hopefully get some new perspective on SSL, get some answers. But also, to follow along. So just feel free to interrupt me. And then, of course, there will be a panel discussion and else. But anything that is not clear, or even if it's just something you maybe disagree on, just interrupt me. And then last thing, so as you saw in the program, there are some big general topics, but roughly how I organized this talk is in two big parts. So the first part is gonna try to bring some general intuition about self-supervised learning. It's gonna be a bit more high level, trying to understand roughly where does this come from and what it's trying to do. But it's not really going to tell you exactly how to make it work in practice. It's more to get intuition and to understand what is SSL in general. Just in case there are some questions you have around that. And then the second part of the talk would be more about practical guidelines and getting those good numbers on for papers and submission. But the first part is more high level and trying to understand what is SSL. So throughout, feel free to interrupt me. And also just to give you some background, so most of the things I've done in SSL are on natural images, video, some time series. And so my goal also is for me to learn about Earth observation data, and hopefully we can exchange together so that you can learn something in SSL, I can learn something on Earth observation, and maybe we can even start collaborations from here. So as I said, the first part, we're gonna see roughly what is SSL, maybe how to derive it from some first principles, and then different versions of SSL that currently exist. And also, you will see in all the mini projects that you will see later on, there will be implementations and everything. So hopefully those slides plus the implementation you will have access to will put you in a really good spot to do SSL on Earth observations. So the first thing is, why should you care about self-supervised learning at all? And there are obviously many different reasons why this could be the case or should be the case. One really pragmatic one is just if you're interested in having some state-of-the-art pipeline. If you look at pretty much any data set, at least for natural images, so here, for example, it's an ImageNet data set, you see some images on the left. It's a really simple task. You have pictures from 1,000 classes, and you try to predict which class is it. And those are really fine-grained classes, for example, which species of dog, type of boats, things like this, natural images. And if you look at official leaderboard, you have a leaderboard for different pipelines and how they perform on this task, you will see that most of the first solutions are some self-supervised learning solutions. Of course, you have many different variants and so on, but they are all different variants of SSL. So first, if you are interested in just pushing the performance of, let's say, AI pipeline in general, self-supervised learning is one of the most popular strategy to do so nowadays. And then another possible angle you might have to approach self-supervised learning could be to try to use that as a general principle to learn representations about your data. So I'm sure you've seen, especially recently, a lot of news articles about trying to learn some general AI, roughly speaking, a pipeline that you can feed any data in. You can ask anything and it will spit the perfect answer to you. And among all those pipelines, at least at one point, if not the whole thing, you're going to have some SSL components in it. So it's really something that you need to be at least aware of and understand so that you can at least understand what those guys are doing and then iterate on it if you want to. So those are probably two of the main motivations why people get into SSL. And of course, maybe the first thing to do is to say what is SSL in a general scope within ML. So of course, it's really loosely speaking one way to think about it. So within this huge area of machine learning, so whenever you have some learning happening from your data, you can zoom in a little bit and look at unsupervised learning. So where you don't have any labels, you just have raw observations. And then within that, you can define self-supervised learning. So the goal is really to try to learn something from your data without having access to labels at all. And so this is great because just from this, you can already understand why there is so much interest in SSL because you remove the need for labels, which are costly. You need experts to label everything. And it's not just about cost. It's also if you have labels, you need labels for each downstream task that you want to solve later. Which means that basically, if you want a representation to solve a task that you don't know about yet, supervised learning is not going to be the right approach to it because you don't have the labels yet. So I will also add as a comment that although this is a great, really high-level depiction of what is SSL, I think it's a really short-sighted characterization. And hopefully, by the end of the next 20 slides or so, you will sort of agree that actually SSL is much more than just another unsupervised learning method. But yeah, if you just need a quick mental picture of this, you can use this. So one thing that has been said in the past is that probably one way to learn about something is to actually do it. And so what I will try to do over the next 10-15 slides is to try to understand how can we rederive self-supervised learning from some first principles instead of just throwing at you all the different loss functions that currently exist and try to give some really high-level arguments on why you have this term or this term in it. So we're going to try from first principles, assuming we don't know anything about SSL, to come up with one of the SSL solutions that exists today. And through this, we will hopefully get some nice intuition. So, of course, as you can imagine, there are many different ways you can recover self-supervised learning losses. You can have some really high-level arguments about learning, even human learning, right? Or you think you are doing planning, or you think you are learning representations about the world. But this, again, is maybe a little bit high level, and it does not really give you the precise mathematical tools that you may need for your papers or to be able to prove some things about your losses. So instead, what we will be using is a slightly more pragmatic view. And we're going to try to start from supervised learning and little by little make our way through SSL. So you will see, maybe it's not really clear how this will happen, but through the derivation, it will become very clear. And the goal is that through this, you will also see exactly through the derivation what type of mathematical tools you can use if you need to maybe derive new losses, prove something about your SSL loss, try to prove, for example, what are some hidden assumptions on it, what are some limitations. And also it's a great way to get some intuition. So we're gonna follow this path. And again, this will involve a couple of really simple derivations, but the goal is that this is approachable by everyone. So it's just really basic linear algebra. I put all the derivation. And yeah, if you have questions, just interrupt me. So let's start on from supervised learning. So as I briefly mentioned before, the simplest case, right, is that you have inputs, here images, and you have targets here, which are from two classes, cats and dogs. And this is what your training set looks like. So this is given to you. Someone derived those labels, took those images, and that's what you have access to try to learn the representation. So just for notations, we're gonna define by X the inputs, so really standard, nothing special here, and by Y the targets. And we will also define by capital N the total number of samples you have in your training data. So the first thing, given this data set, that people will be doing is that you want to learn a model, so f of theta, that will be able to predict these labels that we saw before, cat or dog, given the original input images X. So if you were maybe 20, 30 years ago, you would probably not use DeepNet yet. Maybe you would do some SIFT features, whatever, and then use a kernel SVM. But nowadays, what you will do out of the box without even trying any baseline, that you will derive some DeepNet architecture, probably for images, take some ResNet or visual transformer. And those usually have this sort of parametric form here. So here I just put a really, really simple example, which would be a simple feed-forward network with ReLU activations. But basically what those are, I'm sure you're all familiar with it, is just a composition of affine transformation and nonlinearities. And this entire input-output mapping is your deep network. It's parameterized by those parameters, W1 through L, and the biases as well. And the whole point of this is that you can learn those parameters by minimizing some loss, for example, with gradient descent, so that after training, the output of your network predict as good as possible the targets that you were given at the beginning. So of course you do this on the training set, right? Then you have all this question of regularization, generalization, because you want this, you want the predictions to be good, not just on the train set, but on the test set, but that's another story. The main point that we care for this talk is that you have some parameters theta, you try to minimize your loss. Here I just put mean squared error, but it could be something else. If you want to predict probabilities or categorical variable, it could be the cross entropy. Again, this would not really matter for this talk. But the point is that you have a loss, you do gradient descent, you learn your parameters, and you end up with a nice neural network that hopefully gives you the prediction that you expect. So this is really basic supervised learning, right? Nothing special about it. So the first thing is one cool question. Can we do better than gradient descent on the parameters to try to minimize the loss? And so this is a really, let's say, pragmatic question, right? And so, of course, so some of you may have some ideas. Do you have any idea on what you could do instead to get the optimal parameters? It's not a trick question. So one thing you could think of is say, okay, instead of doing just first order gradient descent, you can have second order optimization, right? Maybe Newton method, thing like this. But actually, without going that far, one thing you could directly do is figure out. So if I just come back to make this very clear, here, right, the last layer of your deep network is just a linear readout layer, right? You have this W matrix that multiplies the output of the penultimate layer, and then you add the bias. And this is your prediction here that goes into your mean squared error. So the first thing you could say is that, okay, because I know this is just mean squared error, and this last layer is just linear with respect to the penultimate layer of the deepnet, I can find the closed form solution for those two guys, right? This is just like OLS. I'm sure everyone is familiar with it. This is very easy to derive, and it's known. So that's the first thing we're gonna do. So because we will solve them analytically, we will remove them from the network, and we remove them from the learnable parameters theta. We will treat them separately because we will have them in closed form. Also, just for some simplified notations, we will work with the matrix X of inputs and the matrix Y for the targets. And we will denote by F of capital X the matrix of predictions. So again, this is just for notation so that we don't have to keep around all the n indices, the sum over n, etc. And then one thing that will be convenient, again, to simplify notations, is this centering matrix, which is a big n by n matrix. So what this thing does, it's identity minus this huge constant matrix. What this does is that once you do matrix vector multiplication with it, it will just remove the mean from the vector that you multiply. So basically, it's really easy to see, right? You have so if you multiply this thing by x, for example, or whatever vector, it will, the identity will preserve x, and then minus, so you remove from it the average of x. So this is just a centering matrix, and this just removes the mean from the input argument, right? Is it clear? Great. So now we can do this optimization. Like we said, we try to solve for W capital L and B capital L analytically. So again, just the last linear readout layer of your deepnet. Let's try to get that analytically. So the first thing we can solve for is for the bias. So again, this is really easy to derive, and I'll put all the details here, but you can basically take the gradient of this with respect to B, and then you solve, you set it equals to 0, and you have the closed form solution for what the optimal B should be. And it is given here. So you see, I replaced the B capital L value with its optimal value, and it's just the average of this difference. So the difference between your prediction with W and the true target. So far, nothing crazy. You can just get that analytically. And just to simplify a little bit the notation, you can rewrite this thing here in terms of this centering matrix that is defined just above. And so you can simplify it this way. So the problem, now that you optimized for B, becomes really simple. You try to still do this regression problem, right? You have a W capital L times the output of your network that you center through this matrix H. And then you try to predict the centered target matrix Y as well, right? So again, this is just by rewriting this line here in terms of this centering matrix. And this came from plugging in the optimal value for the bias vector B. Okay, so now you just work with everything that is centered, and you still try to minimize this Frobenius norm. So the next thing we do is that we can solve for W. So again, this is just the least square solution. You can derive this analytically in just a few lines. You take the derivative of the Frobenius norm with respect to W, you set it to 0, and you obtain this closed form solution. The only hidden assumption I did not put explicitly is that this matrix is invertible, i.e. the output of your deep network here is full rank. But in most of the case, even at initialization, this would be true, and that's the only assumption here. If not, you can just remove the dimensions or the parts of the vector space that have 0 for their singular values. But we don't need to go into that. You can just assume it is full rank. And so in this case, you have this closed form solution. So this is the optimal W, right? I just found the solution to it and plugged it back into this equation here. So far, again, nothing special, right? We just solved for B, rewrote in terms of this centering matrix, and then solve for W. So it's just like the usual mean squared error with a deep net, except that for the last linear layer, we use the optimal parameters that we can get in closed form. So this, is it clear for everyone? Yes. Yeah, so the optimal value of the bias, which is plugged in here, it's this value, can be, then once you rewrite it in terms of the centering matrix, the expression becomes this. So this was the optimal bias that was plugged in. And then you have this y here multiplied by this term, and then minus this y. So you can just rewrite it as y times this centering matrix. So you just plug the optimal value of B, rearrange the terms, and you go from this to this. Good. So here, that's what we end up with. This final, yeah. Correct, yeah. So now this f of theta, we remove the last linear layer from f of theta, which is the network. So basically, the original deep net, you had this linear readout layer, but now because we want to solve for those parameters analytically, we remove the linear readout from f, and we solve it analytically. So now, this is the expression that we had, which was this mean squared error in terms of the optimal W and B. So the next thing we can do, so this is just a reprise of the previous equation. We can again simplify this. So don't be scared with the length of the equation. There is nothing special here. It's just extending the Frobenius norm in terms of the input arguments. So you have the Frobenius norm of each argument minus 2 times the trace of each argument, one transpose the other. So this is exactly what you have here, the Frobenius norm of this term here, then the Frobenius norm of this term here, the left one, and then minus 2 times the trace of this guy transpose times this guy, or vice versa, the same thing. So this is just deriving the Frobenius norm. Nothing has been done yet. But the nice thing that will come in is that the Frobenius norm here, this one, once you simplify it, it will just recover this term here. And because of this full thing simplifies as this equation. So again, because this one will become the same as this one, the minus 2 plus 1, so you have just 1 left, which is minus 1 over n, this trace. So again, this is, you can just derive it by n. It's really easy to do because again, we call that the Frobenius norm of a matrix A is just the trace of A transpose A. So you can just rewrite like the trace of this transpose itself. And once you simplify things, because you see you have like f of theta x h, and then you have another f of theta x transpose that will come in from the transpose, it will simplify with this guy, and so on and so forth. And so this thing will just become equal to this thing. So very easy to derive directly. And that's the final form of the expression that we obtain. So again, here we did not do anything special, right? We just took this mean squared error with the optimal readout parameters, linear readout parameters, and we are just simplifying what this expression looks like, just direct calculus. Now we start again from this expression, and by the way, it's the last slide of derivation, so bear with me. We start again from this equation, and we can again further simplify it because of this term here. You see you have the inverse of f of x transpose, and then times f of x transpose f of x. So once we rewrite f of x times h in terms of this singular value decomposition, so you have the left singular vector, singular values, and right singular vectors, then this expression here, this trace, again simplifies this way. So the final expression that we get is this term which is not a function of theta. So we don't really care about it because we want to learn theta, right? So we can ignore it for now. And this term here. And this term is really interesting because you see you have Y transpose Y, which is a target matrix, right? So Y is a target matrix. So what's Y transpose Y is this big n by n matrix that tells you how similar are the targets between different samples. And this big n by n matrix is multiplied by this other big n by n matrix, which comes from the product of the singular vectors of your representation. So basically what this does is it compares all inputs relates to each other in terms of the target matrix and how inputs relate to each other in terms of your representation, the output of F, basically. So you try to compare those two big intersample relation matrix. So this is just, again, supervised mean squared error, simplifying the linear readout layer, putting the optimal values for the parameters and simplifying the equation. There is no simplification or no assumption whatsoever. This is just rederiving the loss as is. So is this derivation clear? This will be like one of the key things of the first part. So if there is anything not clear, just feel free to let me know. Yeah.
The one thing that I didn't quite get, how did we get the optimal bias?
Oh, yeah. Sure. So basically, when you start from here, so let's say you want to get the optimal bias. So you see the expression is quadratic in terms of this bias. So we can get an optimal closed-form solution. To do that, we take the derivative of this expression with respect to the bias. And then we set this derivative to 0, which will give us the optimal value for B, which is given here by this expression here, without this right one, which is here. So the expression for B is this one. So the difference between the matrix target Y, the current predictions, you take the average of that. So you see you take the average because you multiply by this vector of 1 and you divide by n. So it's just taking the average. And so this is the optimal value for B. So the whole goal of B is just to see, okay, what's the difference between your prediction, the target? I take the average of that, and this is my optimal value as B. Okay. Yeah.
Why was it important to this math?
Yeah, so we did not remove the last layer from the full prediction pipeline. We just removed it from the actual network because now we make it explicit so that we can solve for it. Because you see, so before, the way we define the network was that you have a whole bunch of layers, which are affine transforms and ReLU nonlinearities. And then the last layer is just a linear readout layer. You multiply by Wn and you add the bias BL. But now, because we want to solve for those guys, we remove them from the definition of F theta. So F theta will just be the same thing, but without W and B. And instead, we explicitly multiply and shift the prediction with WL and BL. So we did not remove it from the whole prediction mapping. We just remove it from the definition of F theta so that we can solve for them analytically here. Good? Yes. Yes. Yeah, sure. So here it's the same argument as for B. So basically, here you have this expression, right, which is a quadratic form, and you try to get the optimal value for W. So you can take the derivative of this with respect to W, which gives you some expression. And once you solve that, this equals to 0, which will give you the optimal value for W, you obtain this expression right here. And this comes from the least square optimal solution and is just solving for what is a gradient of this with respect to W is equal to 0. So it's really direct to derive. You can find, so for example, you search online what is the derivative of the Frobenius norm of a fine mapping, because this is a fine in W. You have a really simple expression. You solve this equals to 0, and this will give you this expression right here. Good. Great. So yeah, so basically, so you saw we just we really did nothing crazy. We just solve optimal parameters of the last linear layer in a supervised mean squared error, and then simplified the equation, and we obtain this final form here, right? So why is this interesting? So again, we went from this expression that, if you think about it, this one really treats each sample sort of independently, right? You have for each X, you process it through your deepnet and your linear readout, and you see how it compares to your target Y. And then you have this mean squared error that tell you how good your prediction is, and then you get the gradient from that. It tells you to change your parameters. But in a sense, you have this one-to-one X to Y prediction, and it's sort of treating each the sample independently from each other. But on the right-hand side, which again is the same thing mathematically, we have this new way of thinking about the loss, which is by comparing how the relation between the samples as defined by the target matrix is related to the relation between the samples as defined by this expression here, which is basically the prediction of your network. So suddenly it's not about 1x to 1i, it's how the inter-x relation relates to this inter-y relation. Does this make sense? Is it clear? Right. So this is really interesting, and already, if you're familiar with self-supervised learning, you can sort of get a hint on where we are going with that. But yeah, to me, it's already quite interesting that we go from this, again, just through those derivations. So, of course, some of you might say, okay, this is nice, but maybe there is some hidden assumptions or whatever that you threw under the carpet. So I'm not gonna really trust you, So of course, and by the way, this is like a nice thing to do all the time, whether it's for your papers or when you read the papers, always do some empirical implementation of what you derive and verify that whatever you did for your derivations actually holds. And that's what I'm showing here. So basically, just to be very clear, what I will do is that instead of solving for this analytically, I will just take this expression here and then solve for W and B with gradient descent. So I will solve this with, for example, Adam optimizer, like a really standard thing. And then I will compare the final value to what I derived analytically. And we want the difference of those two things to be as close to 0 as possible, meaning that our derivation actually holds. So this is what I show here on the right, the difference between this optimal form that we found and the value during the optimization that we get. So you see it's going down because you start from a random W and B, and then you do gradient descent. So little by little, the optimal value of W and B goes towards what we actually derive. And so the difference between those two quantities eventually goes to not exactly 0, but something that is close enough to 0 up to like machine precision to say that indeed the quantity that we derive makes sense. So hopefully, if there was anything that you were maybe a bit skeptic about in the previous derivation, this gives you a little bit more confidence to trust these things that we derived. Right? Is this plot? Yeah.
The first part of it is that static now, you're only learning W.
Yeah, exactly. So we just take this expression and we only learn W and B. F of theta is kept frozen. Yeah, so we start from random, you mean the first part, F of theta? Yeah, here I have a random F of theta. So it's just here it was just a 2-layer MLP with random parameters. But you can repeat this process here either with a train of F of theta or like multiple initialization to convince yourself. But here, yeah, I just use a random F of theta. So this basically shows you that indeed this quantity that we derive by n is correct. Okay, so let's think again about this, per sample and inter-sample relationship visually. So again, we started from this X to Y correspondence between here images and target labels. And then through those derivation, we said, well, instead of thinking of supervised learning this way, like each sample independently, we will reformulate it. And again, it's not we, it's just like mathematical derivation, in terms of this inter-sample relation matrix. And the way to interpret it, at least in this case, because we have absolute labels, is to say, okay, instead of saying this sample goes to these labels, instead is to say, okay, those two images are the same or those two ones are not the same, right? And it's really easy to see because when you do this product with a target matrix, so here, for example, Y is just a one hot with the class that you want to predict. When you do this and you have the same classes, this Y transpose Y will be 1. And when it's not the same classes, it will be 0. So when you look at this big n by n matrix, Y transpose Y, and you look at entry ij, it basically tells you how similar are sample I and j to each other as measured by the inner product between their label vectors Y's. Right? Is that clear? Yeah. Yeah, so basically all of this, all the same, is just that when you do this product, it's not going to be 0, 1, it's going to be a real value. But it's the same thing. So when you have your, so for example, for two samples that have almost the same target Y's, then once you do the inner product, you will have a really high value, right? Because the two vectors are aligned with each other. And if you compare two samples that have like orthogonal targets, once you do the inner product, it's going to be 0. So it's the same thing, except that instead of being same as and not same as, it's going to be a real value as well. It's going to be 0 if the two prediction vectors are orthogonal, and it's going to be closer and closer to 1 if you have normalized Y's as the two align together. But in both cases, you can interpret this as telling you how similar those samples are in terms of the targets that you have associated to them. Okay, so just to see if you followed, can you tell me for each of those big Y transpose Y matrices, how many classes I have in the classification task? And again, there is no trick question, right? Yeah, for the first one too. Yeah, exactly. So yeah, I think once you got one, it should be pretty easy to generalize. But yeah, exactly. So you see, this is really interesting because also this shows you that you can sort of understand a little bit more about your problem just by looking at this inter-sample relation matrix. And as you said here, it may look trivial because you are in a classification setting, right? But if you add regression targets, it's also really interesting to look at this matrix, again, assuming you have those target-wise, because it shows you roughly how clusters should your representation be as a function of the inter-sample relationship within your Y's, within your targets. So this is something that, in general, is always nice to visualize if you can. But yeah, what you got from this is that this fully determines, as we saw before, your task that you are trying to solve. So just one last thing before we circle back to self-supervised learning. So one benefit of this, if you are, so suppose you are only a pro supervised learning person, right? And you don't want to hear about anything else. Still, this derivation is quite interesting because what we did is that we said actually to learn a good representation, we don't need absolute labels, which tells me for this X, what is the target Y. Instead, we simplify this task to say, okay, what I need to know is how similar are the labels of those different samples. And if you think about it, it's a much simpler task, right? Because here is an example. So before, how you will get labels is that you have to take someone, pay them, usually as little as possible, show them an image and say, okay, what is the label of this image? But if it's a really complicated task, right, like for example, you have to figure out what is the species or the subspecies of a dog, then not many experts, or at least me, I will not be able to do it, right? So it reduces the pool of experts you can use, and therefore it increases the price that this will need to be allocated to. So this usual supervised way of labeling is really costly. But here, suddenly we said, no, actually, you don't need to have this absolute labeling. You can instead give pairs of samples and ask people, okay, are those two things, should they have the same labels or not? Although you don't know what is the absolute label, right? So for example, you show me two pictures of dogs. You ask me, are they from the same species? Instead of asking me, what is the species, right? So it's a much simpler task. And this means that even if you were just interested in supervised learning, you still should think about this sort of relative formulation of supervised learning, simply because it's going to become much cheaper to obtain labels to solve this task. And again, you have to recall that you don't lose anything by doing that. We show that the two losses are equivalent. So basically, you still get the same really high quality representation, but suddenly you can get away with much cheaper labels. So of course, it's not a general rule because now you have more pairs of samples to ask, but this is a nice alternative to keep in mind. And also, just one interesting thing to point out is that, you know, when you do those sort of like CAPTCHA things, whenever you want to log into a website and you have something that says, okay, verify that you are a human, and you have to say, okay, which pictures contain this object, or which picture looks like the other, which one has the same alignment, you know, things like this. What you are actually doing is providing this sort of relative labels that then people can use for whatever. But this is also something that is really interesting about this approach, that because you remove the need for expert knowledge, suddenly you can just have anyone do this sort of relative labeling, and you can do it at scale. You can just deploy it on your website, and everyone who tries to log in will have to give you labels for free. So this is also something that's quite interesting to keep in mind. Although, again, we are still in a supervised setting, right? So, of course, now you might wonder, okay, this is interesting, but it's not what I came in for, right? So where is self-supervised learning within this whole derivation? And of course, if you are familiar with SSL, you may already get some hints, but the main point that the next slide will show is that actually this whole way of thinking about labels as intersample relative similarity is gonna really, really naturally lead us to self-supervised learning. So now we are just gonna start again from this relative supervised learning loss and show in just a few steps that we just directly recover one SSL loss known as VCREG. So really simple step. First, we start again from this loss that we derived before. Yes. Oh, sorry. Yeah. We are gonna do it with this time is 2 steps. We'll see next time how many steps I need. You know.
But wouldn't it have to be a lot cheaper to get? It's like the relationship matrix is like the number squared.
Yes.
So if you have 1 million images that you want to label,
yeah.
It have to be a million times cheaper to make a label using like the relationship of saying what it is. Like,
good question. So good question. So you have n squared pairs compared to n absolute labels that you need. So depending on the task, it may or may not be true. For example, if you go to like medical things and all, maybe not. And as you said, as n grows, as the relative gain of using pairs may reduce because it grows quadratically and not linearly. But if you use things like this, for example, it shows that actually you don't need to query someone with only a single pair at a time. You can give a pool of 10 images, for example, and just say, okay, which ones are similar to each other? So suddenly you can reduce this quadratic growth to a much better rate. And you can do this through this sort of querying where you do it per group. Because if you think about it, so if we just go back here. So if you think you have only 2 classes, you see it's a pretty dense matrix, right? Like 50% of the matrix is full. But if you think your task will have a ton of different classes, it's an extremely sparse matrix, which means that when you sample a pair of images, it's going to be, and it's like IID, it's going to be really likely that it's just not going to be related to each other. So you can think of this to do sort of smarter querying and not just ask for any random pair, is it related or not? Because here you already know with like 90% chance the answer is no, it's not going to be related. So in this case, for example, what you could do is give a batch of 10 images and say, just find me 2 that are related to each other. And this way already you reduced n by 10. And now you are still quadratic, but in this n divided by 10 space. So suddenly it makes it much more tractable. So yeah, that's true that you cannot say in all cases this is going to be better, but you can always try to find ways around it. And yeah, in some cases it may not be. If it's like really cheap labels, like a cat versus dog, then you can just ask for the absolute labels directly because you don't need expertise at all for that. Okay. So going, yeah.
What other activities? What other
yeah, so basically this, so of course, here we derive thing in a supervised setting, but we will see that it's related to SSL. And the point is that you can use this to do pre-training to get the good representation that then you can use to do one-shot learning. So the point is to use, so of course, here it was all in a supervised case, so you may not see yet the point, but let's assume that you can do this without labels. The point is that you will be able to use this to get a f of theta that is really strong, learn a strong representation, and you can use directly to do 0 or one-shot learning. But yeah, you are true that if all of this was just in the supervised setting, then maybe you are better off just doing some unsupervised representation learning and then one-shot learning. But the whole point of this is actually that this whole thing we derive is going to become self-supervised learning. And therefore, this is what you should use to do pre-training, basically. So this is going to be answered in basically a couple of slides. So here, recall, we start again from this, for now, supervised loss. This is exactly the same as what we derived before. I removed the Frobenius term of y times h because it's independent of theta, we don't care about it. And then instead of minimizing minus the trace, I maximize, again, same thing. So this is just our supervised loss. This is this intersample target matrix. And this is our estimated intersample matrix in terms of those singular vectors. So the first thing is that we don't want to optimize this directly because you need to do a SVD, which is costly. You don't want to do this at each mini batch. And also, the SVD is not really backprop friendly So you don't really want to use this as your learning bus. So the first thing to do is to say, okay, instead of predicting a representation f of theta and then computing its SVD, what if I just use the DeepNet to predict the singular vectors directly? And this is actually very easy to do. You just need to make sure that what you predict are singular vectors. And this condition just says, okay, each of them should have basically norm one and be orthogonal to each other, right? So basically, instead, again, of using the singular vectors, we use the output of the network directly, and we add this constraint here, this regularizer term that says, okay, sure, but make sure that those things that you use for your predictions correspond to singular vectors, right? Is this good? Okay. So this, again, are the same thing, assuming you minimize this regularizer term. This is just to make it more, let's say, SGD friendly. Then we just reorganize some terms. So basically, this is really trivial, right? Because you have your representation, this centering matrix, times the representation transpose. So this is just the covariance of your representation. And then you have this trace here that you can, instead of putting it as a trace, you can express it here as a double sum of the difference between your predictions for sample I and sample J, weighted by the entry of this matrix. So this, again, you just do a few lines of derivations, and you can show those two things are equal. No simplification, is just direct calculus. It's just rewriting for our own sake of interpreting this loss, right? Is it good? So now if you are familiar with SSL, it should really give you some first hints. But you see, you get this new loss, again, for now, in terms of this target matrix Y transpose Y. So we are still in the realm of supervised learning, but we just made it SGD friendly and then slightly rewrote it so that it's something we can easily interpret. Now, the last thing, which is the last missing component that will just from this flip from a supervised to a SSL setting, is to say, okay, this is all interesting, but I don't want to have to access this Y matrix because those are the labels. I don't want to have access to those labels, right? That's the whole point of doing self-supervised learning. So we need to think of a way to have a proxy for this inter-sample relationship. And this proxy that we can call G is going to be what I will use instead of this Y transpose matrix. And again, what you have to recall is that the whole point of this Y transpose matrix is to give guidance to the network as to which samples should be close to each other in terms of the semantic or in terms of the labels that is associated to it. So that's really what you have to keep in mind when you try to derive a proxy for it. And so what you do if you are doing self-supervised learning is that you define a proxy this way. So first, you take your original data, X, and you will say, okay, I know some data augmentations that should preserve the same label. So again, you don't know what is the label, but you know that, for example, if you just translate a bit the image, the label should be the same. It could be also a flip. So for example, just going back very quickly to this example, you see those two things have the same label, and the only difference in the image is maybe some coloring and then some small rotation of the object. So you know, without having to know the label, you can know what sort of transformation you can apply to X so that you keep the same labels, right? Is this clear? Great. So using this principle, what you do in self-supervised learning is that you will derive this sort of new augmented data set with those augmentations that are here in this operator T. You will create V views. What we call views are basically different representation of the same input that should be associated to the same target. So you preserve the semantic of the input. And then, because of this, suddenly it becomes really easy to derive a proxy for Y transpose, because you can just say, well, at least one thing I know is that all those guys should have the same label. And therefore, for those entries in G, you can just say, okay, if you come from the same input, so you are different views of the same X, then I will put a 1 in this matrix. Otherwise, I put a 0, right? Is this clear? This is a key bridge, let's say, between all the derivation we did and self-supervised learning. Finding a good proxy for this relation matrix. And one way to do it, or one popular way to do it nowadays, is to do it this way, generate different views, and put the corresponding entries in G as 1. Good. So if, for example, you use only 2 views, so in this case, you usually refers to those X's as positive pairs, because they are only pairs, you have only 2 views, and positive because they have the same label, so they are like positively related. Then you can rewrite this supervised loss that we saw before in terms of this proxy graph G, and you obtain this loss. So again, this is a covariance term that, yes. Yeah. Mm-hmm. Yeah. Correct. Correct. Yeah. Yeah. You will have missing entries. Yeah. Exactly. So basically, in general, it's going to be really hard to recover Y transpose. And in fact, in general, you don't want to recover exactly Y transpose, because if you do, it means you will just sort of overfit to this specific task, supervised task. And the whole goal is that you actually want to have a good proxy for it. So you still learn something that preserves semantic similarity, but you don't want to overfit to any specific supervised task. This is what is going to give you a good general representation that then you can use for like one-shot learning and other things. So that's why when you derive G, you should try to find a way to have good intersample relationship for the ones that preserve the same semantic, but still you don't want to go all the way and recover one really specific supervised task. Otherwise, you will overfit to it, which may be good in some cases, right? Because if you want to use the representation for that downstream task, right, it would be good without any fine-tuning. But if you just want a general purpose representation, you just want to find the general enough G so that you have a general representation to serve many downstream tasks. But yeah, if you were to think of a given task, a given set of data augmentation, then you will say, yes, you have missing entries in G. Yeah. Good. So, yeah, so then you can rewrite these laws that we saw before using this proxy for Y transpose and the way we construct the dataset with the data augmentation. And we obtain this formulation here. So yeah, the covariance matrix we already added before, now that we just compute it on the set of augmented samples. And then you have this term here, which is basically comparing the 2 views of each X and tries to make them close to each other in terms of this L2 loss, right? So again, this is just using the loss we derived before, but plugging those special cases into it, right? So now notice this loss does not use any labels at all, right? Good, okay. So basically, through all of this, what we pretty much did is that we recovered one SSL loss called VCREG, which is used. It's one of the many alternative losses that we will see later, but it's one SSL method. And the way we derived it was by starting from the supervised setting going into from absolute labels to sort of intersample relative labels, and then finding a good proxy for this YY transpose matrix so that we can remove the need for labels, right? So is this whole derivation clear? Great. So basically, from this, hopefully, you should already get a lot of intuition into what self-supervised learning is doing, is trying to find a way to derive a proxy matrix that tells you how semantically similar are different inputs, and use that to learn a representation. So yeah, basically, this is what we showed. And of course, depending on how you define this proxy, whether you use data augmentation or not, this is going to change the objective and the representation you learn. But one way you can think about it is that it will do so in the same way as if you were changing the labels of your supervised task would change the representation that you learn, right? So yeah, hopefully you saw through those derivation what could be done. And this type of derivation is also really interesting because then you can see some conditions, when does it fail or not, or for example, what constraint you may have on G, and so on. So it's always useful to keep that in mind. So, of course, now you may wonder, okay, this is great, but we derived a lot of things that maybe it's not really easy to derive if you don't have knowledge a priori, right? And this is a bit tedious. So if I want to solve problem, you know, this does not sound like a really interesting approach, right? So of course, in practice, when people come up with new losses, they won't usually go through the trouble of starting from some known objective or loss, and then try to find their way out of this Y matrix. Instead, we can identify from the derivation we did, people rely on two really core principles that are present for all, or I will not say all, but most of the SSL losses, which is that you have a combination of two key terms. One, which tries to collapse similar sample, collapse as in bring together in representation space. And then, of course, another term, because if you have only this first term, then it's really easy to have a degenerate solution and your network just predict a constant, right? Because then you will completely minimize this first term that says, okay, for the samples that I know are similar, I should have the same prediction. You can do this by just predicting a constant regardless of X. And this is not interesting, right? If you have just a constant representation, you cannot solve any downstream task. So then you have an extra term which says, okay, sure, you can try to collapse as much as you want those samples that I tell you are related through this G matrix, but also don't have a representation that overall collapses to just predicting a constant. And this is just putting into words this equation that we had here, right? So this term here is the one that says, okay, if the two samples are similar, then I want them to be close to each other after mapping through F. And here, close to each other is measured in terms of this Euclidean L2 norm. And in addition to that, you have this term here, which says, okay, you can try to collapse as much as you want, but still the covariance matrix of your representation should be close to identity, i.e. Should be full rank. So this is how those two terms look like for Vic-Reg. And you can really easily see from here that if you have only this term, then you can just predict a constant for any input, and this will be minimized. So you need this extra term to prevent your representation to just be a constant value for any input, right? Good. So in practice, what most of the people will do is that they will use those two core principles, and then just based on this, you can come up with your own loss versions. You don't have to do any sort of derivations or anything starting from a previous loss. You just try to combine those two things. And one other thing to keep in mind is that those two terms can be explicit or implicit. And what I mean by that is, in the previous loss, you saw we had this covariance and the invariance term. So those are two explicit terms. But you could have a way to enforce the collapse through some implicit terms. So it could be, for example, because you have batch norm in your network, which batch norm, right, you divide by the standard deviation of your feature, so you prevent the prediction to be constant. So you could have some implicit mechanism that is part of your architecture that will enforce those things. And same for the invariance term, right? So for example, let's say you want to be invariant to translation of your input. Well, maybe you can just do global average pooling or global max pooling as part of your architecture, and that's it, you are done, right? You don't need the explicit term in your loss necessarily, but still, whether it's explicitly or implicitly, you need those two things to be present because one without the other, you will not learn a good representation, right? Again, if you have only this one, you just predict a constant. And if you have only this one, then basically you just do some sort of PCA whitening. You just scatter all your points, but you don't try to bring the inputs that are semantically similar close to each other. And therefore, your representation will not be good for any downstream task. So you need really the interaction between those two terms. So yeah, so as we saw, in VCREG, this is done in a really intuitive way. You have this covariance term and then this invariance term. And then, of course, here I just have the general formula, but then you can think of adding an extra hyperparameter here if you want the focus of the learning to be more on one or the other. And this is one of the things that I will speak about in the second part of the talk. But yeah, once you have those core principles, you can really, you have like full freedom to customize those losses as you want. So for example, one use case is, let's say you don't really believe that your augmentation is preserving the semantics of your input. So you don't want to give too much weight to this term here, because otherwise you will collapse inputs that you should not collapse together. And so one way to prevent this is to just add an extra hyperparameter to weight this term. Just one example. Then you have basically all possible SSL losses that will follow the same principle. So for example, SimClear, you enforce this invariance term through cosine similarity between your inputs. And then you prevent collapse by making sure that you maximize the entropy of your representation. And of course, the entropy is something you cannot get exactly and efficiently for continuous representation. So you have some estimates through the log sum x, etc., that you will see in the SimClear loss. But what it's doing, what you only need to keep in mind is that it's trying to maximize the entropy of the representation, i.e., you should not just predict a constant, right? So this is what SimClear will do. And again, you can see it's really related to each other because here, L2 distance, if you renormalize your input, it's going to be really, it's going to be the same as the cosine similarity. And then here, the covariance is basically measuring the entropy if you assume your data is Gaussian. So those things, although they may look different, they are all trying to do the same thing, and you can even show under some assumptions on your data that those losses are actually exactly the same. Another one, which is interesting because then you have some implicit term. So you have BYOL, for example. So BYOL, you just have this invariance term. So you try to have this cosine similarity between related samples to be high. And the way you prevent collapse is by using a target network. So when you compare the inputs, it's not just for the same f, you have f of tx and f of tx, and you try to make them close to each other. What you have is for one of the two views, you will use a target network, which is basically, let's say, a delayed f of theta during learning. So in practice, you do like a moving average of the parameters that you learn through gradient descent, and this will be your target network. So because you create this asymmetry between the two, you prevent the collapse from happening. And so this is one of the examples I mentioned before, where you have one of the two terms which may be implicit or by construction of your method. Then you have another one, for example, Barlow twins. So in Barlow twins, you will compare through correlation the dimension of your predictions for the two views of all the inputs. So again, you try to make them as close as possible, and you prevent collapse through normalization in the correlation computation. But again, you see the same principle is true for all those losses. And then another one that is quite interesting, it's masked autoencoder, which are just denoising autoencoders, from 2000s with a slightly different augmentation you use for the data, which is masking. So in this case, what you do is that you have an input, you apply this augmentation, goes through your encoder network, and then you have an extra decoder network G that tries to reconstruct the original input. So from this, you see that you prevent collapse because you require reconstruction. So you cannot just have F predict a constant, otherwise you cannot reconstruct each different X from just a constant. So the collapse prevention comes from the reconstruction loss. But because you want to be able to reconstruct the same X from different views of the original input, you still try to make them close to each other in the representation space. So again, here you see through this loss, the way you enforce the invariance and the anti-collapse term is more subtle and implicit. And that's also why one of the reasons why MAE usually is a really good baseline, but it may not be the best thing that will give you state of the art unless you do some fine tuning, because it's really hard to control those terms from reconstruction loss, because, for example, it depends on what type of decoder you use, things like this. So you have extra parameters that you really need to be careful about. But again, the same principles apply to all those different methods. And this will be, so I think you will get to experiment with all of them, but you will see basically that you have the same thing happening in each of them. And then you have different hyperparameters, different learning dynamics, but still the same core principles apply for them. Yeah, so one thing is, so you probably got the message from the previous slide, but if you really spend some time, yeah.
Sorry, I did struggle with the interpretation. So if you look at the very first slide, so calligraphic G, this transformation applies to the input.
Correct.
As randomized?
Yeah, correct. So if you do T of X and T of X, it will be two different views. You have the randomness inside T.
So, that's the covariance of that. So this is the covariance over the function of X and force X.
Yeah, so over the two views of X, correct, yeah. Yeah, so you have... Yeah, exactly, yeah. And so you can show, so for example, depending on TFX, of course, if X is huge, then you may not need the two, just one of them would be a good enough estimate, and so on. But in practice, you will get those views, concatenate them, do the covariance, and then try to make this go to identity. And again, this is for the case where you have only two views. If you have many views, you will have many more of this, right? You will concatenate TX V times, and then do the covariance. But again, if X contains many samples, you may not need to use them all to get a good estimate of the covariance. So those are the type of questions that, for example, if you try, if you are limited in terms of GPU memory, and you try to still get the method running, you can try to derive some proxies or good estimates for this. And that's one of the angles that a lot of people are looking at, because of course, ideally you want to use as big of a network as possible, which means that you are memory constrained in terms of GPU. And if you find good proxies for this, it's always better. because also along this line, this will be a big dimension by dimension matrix, which if you go to really high dimension, this may be too high, right? So then you can think of maybe low rank approximation or whatever. But yeah, basically all of those questions are valid and relevant today. How to make the computation of those laws more efficient so that you reduce basically computational bottleneck. Yeah, so basically, as I briefly mentioned before, all those losses rely on the same core principles, right? So you may wonder, why do we have a ton of them? And in fact, what I showed before, just 5 or 6 of them, is basically nothing. If you have any sort of feed with archive or anything, you will see that you have new SSL losses that come maybe every few days or so. So you really have in practice like hundreds of losses. And so of course, if you just want to start SSL, you might wonder where to start, basically. And so one of the main takeaway is that if you really spend time on your loss, whether it's by introducing an extra weight that you can cross-validate, you tune your data augmentation, things like this, which loss you use does not really matter much. In fact, when you see even recent papers where people spend like 10,000 GPUs for months, you will see that at the end they just beat the state of the art, but by a really small margin. So the long story short is that which loss you pick is not going to be the key differentiator by giving you a plus 20 percentage points in your final performance. So again, assuming you spend some time to make your loss work, figuring out which loss to use is not going to be so useful. But one of the key things is how you design this T operator, if you use this data augmentation scheme to build your views, and how to define this G matrix, which tells you how different samples relate to each other. This is really the key thing that regardless of your loss can make your representation completely random or basically near optimal. So this is where a lot of people spend a lot of time. You have usually have people who specialize in one loss, and then they spend all their time figuring out how to define the data augmentation and how to derive this G matrix, basically. And of course, again, this G matrix can be done in many different ways. Yeah. Yeah, yeah. Yeah, yeah. Yes. Yeah. Yeah. Yeah, that's a great question. So first, I will say if there was a clear answer to this would be probably a really nice, oral paper in the next conference. So there is no clear answer to that. But there are some recipes. So in fact, I have some examples here. But yeah, as you said, in general, what you will want is to build a G so that you try to bring closer together people that are semantic images or whatever that are semantically similar, but not too much either. So for example, it could be, so if you remember this like fish example before, it could be, okay, if you have the same fish that are roughly pointing in the same direction, maybe I want those ones to collapse. But if it's maybe like the same fish, but one in an aquarium and one in a sea, then you don't want those ones to collapse, although they are the same fish. Oh, so this you can do it by hand as well, right? So for example, I think you will see like doing this way. So suppose as part of the data, you also know the localization, so where the picture was taken. And just from this, you could use this to define G. You could say, okay, if this picture is taken at home, then you can use this to make G small to each other because the picture of the fish, they will be like from aquariums, right? But then if you are in the wilderness outside, then it's probably in the sea or like whatever in nature. And so what you can do is that use this sort of meta information to help you build G so that you don't try to collapse everything together either. But yeah, that's one of the big challenges of SSL is how you define this G matrix, basically. And again, there is no clear recipe. And usually, at least the way it's done today, is still really sort of biased. So it's not as much as using Y transpose, but it's still really focused toward a few downstream tasks that are about like perception. But you can find downstream tasks where the Gs that we define today will not work at all. So this is one of the big research questions. And there are many things you can think about, right? So for example, one thing you could say is, maybe I don't care to have the optimal G. Maybe I can come up with 2 or 3 Gs that are complementary to each other. So I will learn 2 or 3 networks. And at least I have the guarantee that for any downstream task, at least one of them will be good enough. So then you can try to have some research question like this, which could be what's the minimum span of Gs that I need to learn so that I can recover anything. But yeah, basically we have all those things that are valid research questions, basically. But still, there are some quick guidelines, not guidelines, but practices that people do. So one thing, for example, is that if you have video or time series data, then you can use that to build G. So instead of saying, okay, I have one X, I apply a data augmentation, another data augmentation, and those guys have a 1 in this relation matrix, you could say, if it's a frame, and those are frames adjacent in time to each other in a video, then I will put a 1 in G. Or maybe in G, I will put some function of the time between those frames, so that it's not just a 0-1 matrix. But you can use this sort of metadata to build G, depending on the type of modalities you have access to. So for example, also if you have spatial data, you can try to use that to build your G matrix as well, right? So if you have pictures that are taken from the same exact location and facing the same angle roughly, then you can just use this to build G. Because most likely it's going to be pictures of the same buildings or whatever. So this can also give you extra information on how to build this matrix. And then again, this can also be used to combine many modalities, right? So for example, if you have image and captions, then you already know those 2 guys are related to each other. So it's really easy to say, okay, the image and caption, so the I and J corresponding to those 2 data have a 1, because I know they are the same thing. The caption just describes the image, what's in the image. So the representation of those 2 things should be the same. So again, the way you build G depends a lot on what amount of information and what type of data you have access to, basically. Yeah, so basically just reinforcing that, the main point of G is to try to encode some semantic relationship between your data. And again, the way you define that depends on what you want to use your representation for a posteriori and what type of data you have access to. But the key is that you should really have G that tries to focus on semantic similarity. And then one last thing I will say related to the design of G is that you may think there are some really simple ways to define it. For example, you could say, okay, I just take my data, I look at how close X's are, and I just use this to define G. But you have to remember that often this type of definition of G does not preserve semantic similarity. And here I showed a really simple example using CIFAR10 images. So they are again natural image, really small, 32 by 32 pixel, really simple, with 10 categories like horse, boats, car, trucks, etc. And what I do is that I look at the distance between pairs of images that come from the same class in green and from different class in red, and I show the histogram of these distances. And you can see that there is no clear separation. So whether the 2 images come from the same class or not, you can have small and large distances. So in short, you cannot use the distance, like Euclidean distance in input space between images to really define a G matrix, because those distances basically have no meaning at all. So this is also one thing to remember, is that you may, so for some data modalities, this may be valid, but once you go to usually high dimensional data, just input space distances are not going to be really informative. That's also something you want to keep in mind when you define G, that it's not a trivial task at all. And you can use this sort of really simple, let's say, like analysis to try to see, okay, is this G matrix relevant or not? If you have access to just a few labels, you can try a few recipes and see, okay, is the G matrix separating those two or not? And this can also be like a nice signal to iterate. But yeah, the task of defining G is still a really open problem. And so just to finish this first part of the talk, basically, you remember at the beginning, yes? Yeah, so good question. So basically, this really depends on the type of downstream task you want to solve. So for example, if you want to do object recognition, you will care about the object itself, but not the position or the lighting of the object or the background. But actually, if you want to predict if you are taking the picture during lunchtime or during night, you actually don't care about the actual object, you care about the lighting. So basically, what you define as a valid semantic similarity really depends on you and how you want to use your representation downstream. But in general, there is not just one answer that says this is a general thing that you want to preserve, because you can always find a downstream task where you don't have this information and you will basically fail completely. So this is really dependent on the type of downstream task you want to look for. So yeah, so just to finish this part, so you remember at the beginning I mentioned you have this sort of general categorization, let's say, or organization of self-supervised learning as just another unsupervised method. But I think through these derivations that we did, you saw that, at least to me, you will tell me if it's something you agree or not on, the way to think about self-supervised learning is really more as a new general framework from which you can recover many different methods, but it's not a subpart of unsupervised learning, because as you saw, if you have so much Oracle knowledge to define this G matrix as possible, then you could just recover supervised learning as well. So to me, the way to really think about self-supervised learning is basically finding a sort of new meta objective, a way to derive new representations that gives much more freedom and from which you can recover many different methods. And in fact, to me, and that's to me the reason why self-supervised learning really is able to outperform most of the other methods nowadays, is that its strength is that it gives more degrees of freedom to you, basically. Before, if you are doing supervised learning, what degrees of freedom you add, maybe the architecture, the loss, but those are really have not a huge impact, right? There is just so much you can do by playing with those two things. Now with SSL, you can still play with those two things, and yet you have a third degree of freedom, which is the definition of G. And this, from this, obviously, you can do much, much more. And so that's really the key, the strength of SSL, and also the weakness if you don't know to do this good, obviously, but that's really the key benefit. So yeah, I think we can have coffee break maybe now, and then we can do the second part of the talk, which is going to be more about practice and how to make this work in real life. So I think now we have about like 45 minutes before the lunch break. But then I saw that the lunch break is 2 hours. So basically we have 2 hours, 45 minutes, right? No, just kidding. So yeah, this second part of the talk is going to be more about some tricks and tips on how to actually get those things working. So you will see a lot of examples and so on. And again, yeah, feel free to interrupt me if there is any question. It will still be focused on natural images, but most of the things you will see can apply the same regardless of the data modality. So hopefully it's going to be useful to you. So as you saw in the first part, there are a lot of questions, right, when you design your SSL loss. Yes?
Just one question regarding the factor.
Okay.
So we've seen this G matrix, and the more samples we have, so it's like n squared. So it will be very sparse if you have like a high hash size.
Yeah, so this will also depend on how you define G itself, right? Or in supervised case, like how many classes you have. But yeah, it could be extremely sparse in practical cases, because if you have a huge amount of data, basically the probability that you have many samples semantically related to this one will be lower and lower. So in general, it will be sparse and it should be sparse. And in fact, that's one thing you can also use to sort of derive a G, is to look at some statistics like this, like sparsity and things like this, to see if it's a realistic model of the world or not. Because in practice, if you have a huge amount of data, you cannot have a sample that is semantically related to everything else, right? So statistics about G can be used to figure out if you have a good design, and in general, it should be sparse.
What about just the size of the matrix? Given we have maybe just a one-to-one relationship between the sample, what does it mean for the learning? Are there some insights from that? If we have more negative samples, or maybe a smaller batch size with a lot of positive samples?
Yeah, so that's a good point. So basically everything we saw was more in like a population setting without mini batch training. Then when you do mini batch, it's really important how you sample the mini batches, because as you said, if you have only positive samples, many of the losses will basically be degenerate. And so that's why you have all those methods with like hard negative sampling and so on. So the way you do mini batch training introduces its own complexities. And this too depends on the properties of G, right? If G is really sparse or not, it will impact how representative is your mini batch. But those are still really open questions. The way people get about it now is they try to get huge GPUs and have a huge batch size, so that what you get is representative of the full G. And most of the methods, when you go to really, really small mini batches, it will be much worse, really unstable. So that's one of the open questions today is, how to have good small mini batches to still have stable learning. Good. So, and one of the slides we speak about this a little bit. So, so the first thing you saw, there are many hyperparameters, right? And you can introduce basically as many as you want. And the question is, how do you select them, right? Because you don't really have supervised task, and it's not as easy as supervised learning. So that's one of the main challenges in SSL. How do you pick those parameters? So obviously, the simplest thing to do, and what has been done at least for natural image, video, and so on, is to say, okay, although I'm not using labels to train, if I still have labels available, I can try to use them for model evaluation. And so what people have been doing is that after you get a trained model f of theta, you just get the representation, you learn a linear probe, for example, so linear classifier on top, supervised, because you have access to labels for at least part of your data. And so you can just use that for evaluation metric of how good is your representation. So this is what you will do, at least for natural images, pretty much all the time. And this is what you do, in this case, offline probing a posteriori of training. So you train with SSL, then you save your model, you save your checkpoint, and then you do some form of supervised validation, which usually is linear probing, can be nonlinear, can be with k-nearest neighbor, and so on. Of course, the problem, there are many problems with that. The first one is that you need to have a full SSL trained model. So this is like a bit annoying, because maybe your stuff collapsed very early, you don't know about it, so you waste a lot of time. And also, the training of G is quite inefficient, of the linear readout classifier, because you still have to forward through F all the inputs because that's what is used by G to do the classification task, right? So you need to forward pass X through F, and then use the output f of X to train G. So even though you think, okay, I just trained a linear model, it's gonna be super fast, in practice, it's still not gonna be really fast because you have to go through F, and it's a really slow process, especially if you use data augmentation. And of course, one other limitation is that this requires labels. So what people do most of the time now instead is online probing. So the way to do it is that the same principle, you will use labels and you will use, for example, a linear classifier on top of F, but you train it at the same time as you train your SSL loss. This way, it's really efficient because you already forward X through F during training for your SSL loss, so you get it for free to train G. And at the same time, you will just train it as the training of F goes. So this will be happening simultaneously. And the only thing you need to be careful about, of course, is that when you have your loss setup, you should stop the gradient on the output of F, the one that goes through the linear supervised task, because you don't want the supervised loss to backprop through F. F, again, is learned only through the SSL loss, so unsupervised without labels. But you just use this representation that you already have cached as a quick way to learn this linear classifier on top. So yeah, really be careful about this top gradient, because if you don't put this, then of course the label information will flow through your linear model back into F, and you will get great performance, but it's just because you are doing supervised learning. So this online probing is done most of the time nowadays. And it's really nice because it gives you signals very early during training. So for example, here you see this is on ImageNet. So this is like 1,000 class natural image dataset with some SSL method. And what you see is that during the training, so through the epochs on the x-axis of the model F, we also train on top online linear probe, and we compare this with the offline setting. So you see the online one is in blue. It will be, yeah, I think it's big enough. So you see that, of course, it's not performing as good as if you do the offline setting, right? Because the offline setting, you freeze F and you train the linear model till convergence, while the online case, they train both of them jointly. So for a given number of epoch, the signal you get is not really comparable between those two, but you get a signal during training, which is really nice, because if your model just collapses, which happen many times, then you can just stop training the SSL pipeline altogether and restart with different hyperparameters or else. So this is a really nice way to get a signal about the quality of your representation. But again, at the beginning of training, because this linear model is trained simultaneously with the F model, the numbers you get may look a bit down. So you should not really think, okay, after 20 epochs, I only have this much accuracy. It means it collapsed. It does not. It's just the way the online probing accuracy evolves. But you see, eventually, the offline and online linear probe just produce the same accuracy anyway. So basically, this is also to say, if you were to do cross-validation on a really, really short training schedule, then probably you want to rely more on the offline linear probe accuracy. But if you train long enough, then both will give you reliable information. And then another takeaway from this is that sure, you can use something else than linear probing. And of course, you would get probably a bit better performances. But at the end of the day, if you just want to do cross-validation or have a quick signal on the quality of your representation, you don't really care to go to non-linear probing. Just a linear head will be sufficient. In fact, usually you would like to have a representation that is good just with a linear head, because it shows you learn the representation where your different classes or clusters are already well linearly separable, which is the ideal case for you. If you have to use a really complicated nonlinear head on top, it means the representation you learn is not really well behaved. So ideally, what you would like to maximize is more the linear accuracy. So of course, it still requires labels, but still, if you have access to at least some labels, this is very useful. And again, remember, you just train a linear head on top. So the amount of labels you need, so you need to be able, so you need to have a validation set just to evaluate what the accuracy will be on it. But because it's just a linear model, if you regularize it good enough, you could somewhat use a train as a proxy for it. Although ideally, you will have a train and test bit. Oh yeah, so this term here is just any of the losses that we saw before. So any of those, so if you remember, right, those huge list of losses we had, those one, this is whatever you decide to use for training, whatever hyperparameter, whatever G, etc. This is just your SSL training signal, your loss. You have this term, and then in addition to it, you have this supervised one with the stop gradient. So the way you do linear probing does not care at all what you put for the SSL loss. So it still requires label, but maybe not as much as if you were using labels for the full model, but still it's gonna be a bit biases toward a specific downstream task that you are using. So it's something that is better than nothing, but not great either. And of course, you can imagine variants of this where you have labels for many tasks. Oh yeah, so basically, when you have collapse, this will just go to random accuracy, which will be like, depending on the number of classes, 1 over it. So it's as if you have random predictions. So you just get a random chance for the validation metric and even the train one. And so usually this can happen, for example, if because your loss is not well behaved, maybe you have one gradient that explode, and so the whole model predicts something constant or random a posteriori. This is like really common. Or if you have architectures like VITs and all that you don't regularize well and just diverge during training. So you will see a sudden huge drop in this metric. So another thing you can do to try to move away from using labels is to try to find some sort of necessary conditions that your representation should have to maybe not be optimal, but at least not be collapsed. And of course, there are many ways to do this. And it's something that you can combine with a linear probe as well. But it would be great to have as many signals as possible that convey the quality of your representation. So one thing you can do is imagine you have endpoints in d dimension. So this will be the output of f theta of x. You can ask yourself, okay, given this setup, how many downstream tasks, and here we only consider binary downstream tasks, so it's like 2 classes, can you solve given this setup? So this will be interesting because ideally, right, you want a representation that can solve as many downstream tasks as possible. If you learn a representation and this number is just 1, then you probably don't get a good representation. So anyone has any idea on what will be this number as a function of some properties of the representation? So for example, let's think in terms of the rank of the representation, right? So suppose the representation is collapsed. So you have just a rank 1 representation. It means that your representation just lives basically on the line. Do you think this is gonna be really useful or not? Yeah, it's not, right? So basically, based on this, you actually have an exact answer to this question that dates from, I think, 60 years ago or something, which is from the Covers theorem. Basically, it states the number of binary tasks that you can solve with a linear classifier as a function of your points and the intrinsic dimension of your representation. and this is this number here. So just here is a plot of what it looks like. So this is the number of tasks in log scale, and this is the dimension, intrinsic dimension of your representation. So you see it grows pretty quickly to a pretty large numbers, but the key insight for us is that you should try to avoid collapse in terms of intrinsic dimension representation. And in general, if you have two representations, one with a higher intrinsic dimension or rank than the other, is going to be one that is useful to solve more tasks than the other. So again, it's a really constrained setting because it's linear separability, but still it gives some insights as to how useful will be your representation as a function of the rank to solve as many downstream tasks as possible. So from this, as we saw, you should favor the representation with higher intrinsic dimension. Yeah. Oh yeah, so basically it's simply counting, so given n points in d dimension, all right, how many configuration of labels you can solve with a linear separation. So basically, if you think of all the possible downstream tasks, it's all the realization of binary labels for each of the endpoints, right? So there will be 2 to the power n of those configurations. Each of them is one downstream task. Let's count how many of them I can perfectly separate with a linear classifier, right? Yeah, exactly. Yeah. And again, so this is actually specific because maybe in practice you don't really care about perfect linear separability, but then this is convenient because it's already figured out number. So this is nice to have. But you can really imagine ways to generalize this so that you can have some condition that will be more general on your representation and that will tell you how informative is your representation to solve downstream tasks down the line. Because again, when you do SSL, most of the time you do it so that your representation will be used in many downstream tasks. So yeah, favor the one with highest intrinsic dimension. And in practice, this is actually quite useful. So here I just show an example of computing the rank of this f theta of x, which is here on the x-axis, and how it relates to the downstream task accuracy on these places 205 dataset. So it's like 205 different places. It's a classification problem on natural images. And so each color is a different SSL method. In blue is vcreg, red is SimClear. So basically you should compare points of the same color together. And so what you can see, so of course it's not a perfect trend, but a general recipe is try to use a representation that has a high rank. And how we define the rank, of course, we have many ways to define it. It can be, for example, the entropy of the singular values of the representation. But we show that it does not really matter how you compute it. In general, you just have this general recipe that is label free, right? It's just a function of f of x. And that at least has some small correlation to how informative will be your representation. So here is also another example. So this is just to show the dataset you use to compute this rank does not matter much. So for example, here you have natural images from ImageNet, which is the one used for the SSL pre-training task. And here it's on a different target dataset. Here it's iNaturalist, and then here it's places. And you see that things align to each other. And this is nice because it means where you compute the rank can be just on the source dataset, which is the one that you are using for SSL training. And of course, as long as the distribution of images do not shift too much, this will already be informative of the rank on the target dataset, and thus how useful will be your representation on the target dataset, right? Because in practice, if you do, for example, SSL pre-training on dataset A, it does not mean that your representation will be used on dataset A, right? It may be dataset B, which is other images. So ideally, what you want is to have a big cover number on the dataset B representation. But here we show that as long as the distribution shift is not too high, you don't need to have access to that dataset B to get this metric. Which is good because like this, not only you don't require labels, but also you don't require to know a priori what will be the X's for the downstream task. So another way to do cross-validation or to figure out, yeah.
So I'm curious what your thoughts are in the idea for also.
Yeah, oh yeah, so it's directly related. So if you think of this rank is just sort of linear compression, right? If you were doing compression using SVD, like low rank approximation, then this will be, this metric will be related to this one. And you could come up with new ways to measure that through compression theory. But this is all in embedding space, right? So it's can you compress f of x, not how you compress x itself. And the goal, again, is here to show that if you can compress it too much, so it's like a degenerate rank, then it's not a representation that's going to be useful for many, many downstream tasks. But on the flip side, it may be a representation that is really, really good only for a few tasks. So again, this really depends what you want to do, right? If you want something that is as general as possible, you don't want to be able to compress it too much. But if you want something that is really specialized to a few downstream tasks, then it's actually good to be compressible a lot, because it means you will need less training data when you do the fine-tuning or the one-shot learning. So this is really balance that you have to figure out a priori, is do you want something that is somewhat good everywhere or really good only at a few things? Yeah. But yeah, there are a lot of questions around this. And ideally, you also want to figure out the relation between the measure of compression and the type of downstream model you use as well. Here we saw it's all true for a linear classifier, but if you use something else, then you should have different metrics of compression, basically. Yeah, so this was one way to give at least a signal of when your representation is basically completely useless or not. And then there is another way to sort of inspect your representation, which is a little bit more costly and let's say heavy to use, but this is something that is used a lot once you reach a good baseline and you want to add a few points of percentage to your final accuracy, is to try to inspect your representation visually. So what you want to do is, after training, visualize what is encoded in your representation and see if you think it aligns or not with the different downstream tasks that you think to solve. So one thing that we did, and of course there are many ways to do this, but one thing we did is to consider a conditional generative model that will be conditioned on the learned representation. So how it looks, it's actually very simple. So let's focus just on the top part here, which is how you sample from this. So it's a diffusion model, so it's a way to generate data, it's a generative model. We condition the generative process on f of x. And the goal is that we want the generative model to use as much information about f of x to reconstruct the input. And then, given that, we can basically reconstruct in input space what f of x is encoding. And when you repeat the generative process many times, what is kept constant through the samples is what is encoded inside f of x. And what varies is what comes from the noise variable. So I will show an example of this just the next slide. But the key point you have to remember is that basically this is a way to visualize, so here in image space, but could be whatever modality you use, the features that have been preserved through F. So training does not really matter for now, but if you have questions about training, feel free to let me know and we can come back to it. But in practice, this is how it looks. So you will have an image X. You use that as a conditioning for your generative model. And then your generative model will spit out a new image. So here, for example, we condition on this image of a dog on a beach. And then on the right of this first row, those are samples generated from the generative model. And for each column, we vary what f is. So here is just a random f. So you see it maybe encoded a little bit about the general color histogram maybe of the image, because you somewhat preserve the same coloring, but there is pretty much no information that has been kept from the image. This is a supervised F, so that was trained on ImageNet 1K. And this is really interesting because you see the constant theme, let's say, between those two images is that you have a dog and it's the same species. And this makes sense because when you do supervised learning, you learn to discriminate between basically dog species, which is one of the many classes. And so the only key features you want F to preserve is just the species of the dog. You don't care to keep the background, to keep like the rotation of the dog and things like this. And you can see indeed that for the supervised case, this is true. So you see the background changes, you go from beach to snow, and it's not facing left, it's facing right. So whatever varies between the images is what is not kept in F. Whatever is constant is what is kept in F. So here you only keep information about the dog species, right? Now, if you go to one of the self-supervised F, so here Dino, for example, but this is going to be true regardless of the loss, you can see that the information you preserve is much richer, right? So you still have this dog, but you also preserve information about the beach and also somewhat about maybe like the time of day and the orientation of the dog. And this is really nice because suppose you want a representation that is not just used to predict which class of dog, but also where the picture was taken. Then you can really see that the supervised loss completely forgot this information, the supervised backbone, while the SSL backbone kept that information inside the representation. Yeah?
So for the self-supervised did we use any augmentation?
Yeah, it was the same augmentation for both. Yeah. So that's a good question. So in fact, that's one thing we can visualize. So to answer precisely the question is because when we do SSL pre-training, we use a projector network, right? So if you look at this generation after the projector network, then you also lose the flip and a lot of information. But the backbone we use is without the projector, right? Because the projector is only used during SSL pre-training, and then we throw away the projector. And basically, I will mention it in a few slides, but basically, once you remove the projector, all the invariants you impose through the data augmentation are sort of recovered pre-projector, basically. So basically, the invariances are learned within the projector network. And because you remove it after SSL pre-training, then you are not invariant anymore. Therefore, the information is kept. But this will become clear once I speak about what is the projector network. But yeah, that's a good point as well. And just here it was the same example with this picture of the Earth, but yeah, same insights called. So you can do really some sort of visual inspection by, for example, giving an original image conditioning and then applying some data augmentation to it and see which representation keep or not the information about the data augmentation. Because this will tell you, is your network invariant or not to this data augmentation? And this can be useful to know if your representation F is useful for different downstream tasks. So this, it's not as big as I thought, but there are some really interesting things. So for example, you see here, so we take this original chicken image and we apply some color jittering. So basically everything becomes sort of greenish. But if you look at, for example, the Barlow twins generated sample, you see that the head is red again, which means that basically in the representation, you lose information about the color of the head of the chicken. Now, is this something useful or not depends on the downstream task, right? But the point is that through this generation and inspection, you can really differentiate between different representation. And this is not the case, for example, for the Dino SSL method, where you see that the head of the chicken is also greenish, which is the same as the conditioning you apply. So already, just from this visual inspection, you can see some differences between different SSL methods. And then, of course, in the case of the chicken, it may not be really informative, but if you do this on your own images, you can get some hints as to which representation is better than the other, just by understanding which features are still present within f of x and which one were disregarded. So this is roughly speaking for cross-validation or model selection, right? To compare different losses, different architectures that you use, or even like different pre-training data sets that you use. But of course, this is just to get a sense of how good is your representation. But there are a lot of tricks that are used to further boost performance. So in practice, you don't just use one SSL loss, an architecture F, try to minimize this, and then maybe do a bit of cross-validation of the architecture of the loss. You have a lot of small tricks that will contribute to really pushing performances. So one of them is a projector network. So basically, the way this works is that suppose you want to learn an architecture F that you think is optimal, and that's what you want to use for some reason. What you will do in practice is that you will not use F directly and pipe it into your SSL loss. What you will do first is that you will add on top of it a projector network. Most cases is just a small MLP with 2-3 layers, let's say 2000 widths. So this F2. And this combination of the backbone and the projector is going to be what you put into your SSL loss. So what you will want is that both the backbone and the projector network collaborate to minimize the SSL loss. You do pre-training with that until convergence or whatever stopping criteria you want. And then after SSL pre-training is done, so after you're happy with whatever evolution of the loss you had, then what you will do is that you will take this projector network and you will just throw it away. And what will become your final representation is just this original backbone F. All right? Yeah.
Why does it work here?
So for MAE, you usually don't use a projector network, you have the decoder directly. And that's why MAE is not really good directly without fine-tuning. You want to fine-tune MAE backbones. While here, because of this projector trick, most of those SSL representation are good with frozen backbone. And the reason for that is because basically most of the, so let's say you don't specify G very well or the data augmentation very well, then you have some sort of bias, right? And this bias will be absorbed within the projector network. And once you get rid of it, you recover a representation F that is, let's say, less biased, i.e. Better in many downstream tasks without having to fine-tune it. But yeah, if you were to keep it, then it will be roughly similar to MAE, as in you will need to fine-tune a little bit so that you can correct this bias that you did not remove from the projector network. Oh yeah, so it's different because the decoder is used to reconstruct as a way to prevent collapse, while the projector is used to absorb the bias of misspecified hyperparameters, basically. But you could argue that in a sense, you can also use the decoder architecture to play with that and try to change the bias you learn in the encoder. But in general, like the core reason why you have a decoder, which is just to be able to reconstruct and prevent collapse, While here, you can still learn good representation without a projector. It's just that you will go maybe from like 70 to 75%. So it's more, the projector is going to give you a nice boost of performance, but it's not critical to learn. While without the decoder, you cannot train MLE, basically. Yeah.
One question about the distinction, where does the back start and end, where does the projector start? I know the game, but similar to transfer learning, where we cover, where we initialize some layers, they five. The distinction here seems a little arbitrary to say, okay,
Yes.
now stop.
Yeah. Yeah, totally. And in fact, you can actually show that for some downstream tasks, you may not want to remove the projector, and for some other, you want to remove actually more than the projector. So this is really a sort of crude recipe that you do. It gives you like around the board, let's say plus 3%, whatever number. But still, if you explore more which layers you want to remove, then you can gain even more performances. But yeah, that's true that the way it's done is really sort of ad hoc, and there are probably better ways to do it. And also, as you said, depending on how you define the architecture of the projectors, this can also have an impact, right? Most of the cases, it's a MLP with really a ton of parameters, so that it's really, you know, sort of a sponge for bias that you can then remove. But yeah, that's a good point. And in fact, I think you will enjoy the title of this paper where we explore that, where we show basically that where you cut between the backbone and the projector can have a really different impact depending on the downstream task. So this is just like a general recipe, but for sure far from being optimal. And in fact, as you said, this is something that already was known for many years in transfer learning, where when you were training a supervised backbone, then you were just either reinitializing or removing the last few layers to try to have better transfer capacity. So this is not something new, but it's something that is heavily used in SSL to boost performances. And in fact, as I said, the whole point is that this absorbs some biases. But if you are able to do good cross-validation, you may not need to use this projector at all. So again, the capacity of the projector and how much of it is a projector is also dependent on how you think your representation will be biased, because you cannot do correct cross-validation. So all of those things are moving pieces, right? And it's not like you should apply it always or not. That's why it's really good to have intuition about what you are doing, because each of those hyperparameters is tied with another one. So yeah, so then another thing, again related to what you just said, is that even if you remove the projector or not, you don't necessarily want to just use the last layer representation for your features. So what is also common to do now is to combine the representation of, for example, the last 3 layers or whatever number. And this will become your final representation to solve your downstream task. Because basically, maybe some of the biases that you have at the last layer will be really good for some tasks, but not for others. And in which case, there will be some part of this aggregated representation that will always be useful for different downstream tasks. So that's also something that most of the benchmarks that you see on the paper do. And just by doing this, again, changing nothing on how you train your SSL pipeline, right? Same G, same loss, same everything. Just by doing this, you get an extra, you know, +1 or 2 points or whatever. And this is really something that is quite nice. Of course, in practice, it's a bit weird because it's not always clear when people use it or not. So sometimes you see comparison in tables. You see a new method, it outperforms a previous method, but maybe it's just because, you know, some of them did this trick, some did not. So it's also something to keep in mind. But yeah, that's one thing you can do and almost always improve performances. Yeah. Yeah, good point. So ideally, so for example, if you have a ResNet or something like this, then you can look at different layers. Which will look at different sort of localized or global features. This is easy. If you have transformers, there is still some gain in looking at different layers because each representation has different amount of, let's say, collapse or biases within them. So there will still be some gain, but yeah, the gain may not be as much if you take, for example, the last 3 layers compared to maybe the last 2 layers and one of the intermediate layers. So this is like one of the open question as well, which features or which layers to extract the representation from. And in fact, to answer that, sorry, comment to the last 3 layers, but to answer that, there are some new methods now. So there is one, it's called head to toe. Basically, the way they do it is that they say, okay, I'm gonna consider all the possible features in the entire backbone. So you have like millions of them. And then I'm going to do some sort of feature selection to see which ones do I want to keep, which ones are the most informative. And you can use like really ad hoc rules, right, based on correlation of the features or things like this. But now you have more and more of those methods coming out because they are sort of a cheap and easy way to get a boost in performances without having to play with different SSL loss, SSL graph, and things like this. So this is also something that you will see more and more, at least in computer vision. And this, again, gives you a nice boost in performance. And you can apply it regardless of your SSL loss. Yeah?
Okay, so if you have several auxiliary data, let's say, where would you use that data? Is it before the data gateway or where would you advise?
Yeah, so that's a good question. So basically, this is really easy to do if you have like a ResNet, right? Because you have your layers, and maybe if you have like spatial information, you can either pull it or not. If you know your downstream task requires spatial information. But for transformers, it's not clear if you should use what's inside the MLP block, what's inside the attention block, or whatever. And so this is also an open question. And there is no real answer to this. It really depends on the downstream task that you want to use and your prior knowledge. And then you may think, okay, I maybe only need to get, I don't know, whatever feature from this token, if you have like a CLS token or whatever, or it may be from all the tokens. But yeah, in general, there is no clear recipe that will tell you, okay, for transformers, this is the key part that is most informative for your downstream task. This is one of the key open questions, even like in LLM, etc., where to extract meaningful features, and it's still completely unexplored. Yeah.
So how much the performance comes from increased number of dimensions, concatenating features.
Yeah. So good point. So usually it's still going to give you better performance to aggregate features across layers and just increase the dimension of the last layer. Because if you do this, basically you still stay at the last layer, which may have a lot of biases depending on how you specify your hyperparameters. While if you look at different layers, as you go closer and closer to the input, as you almost remove everything and you go back in input space. So in general, you will have more benefits by doing this sort of aggregation across layers than just changing the output dimension. And also in general, just increasing the dimension may not always help because then in the limit, it means you need more training data for your downstream task to learn your classifier, right? So ideally, you want to take the most relevant features from different layers, but still not concatenate everything to reach a million dimensional representation. And so that's why in this head to toe paper, you have some feature selection process that's going on because you just want the most informative features, but not concatenate everything either. Yeah.
Talk about bias, for example. What exactly is that bias?
So basically, you can think of it the same as when you specify one label, one set of labels for one supervised task is going to be biased compared to another supervised task which has different labels. So it's similar. If you misspecify G, you will collapse some points together that you should actually separate because your downstream task treats them as different classes. And so the representation that you learn will be biased toward a specific downstream task or another one. Yeah, exactly. Yeah. And it can be a lot of things. It may not come just from G. For example, it may come from your definition of your architecture. So I say something completely random, but suppose only at the last layer, like it's common in ResNet, only at the last layer you have a global average pooling. Now, if your downstream task is to describe the position of the dog in the image, then the last layer will be pretty much uninformative because you removed all spatial information. And so suddenly, if you add features from different layers, you can sort of recover that and get a much better representation. So this may come from many different sources. And so that's why in general, because the search space is so large, there is always some benefit of introducing a projector network and removing it a posteriori, or using features and/or using features of different layers. Yeah. Yeah. Yes. So in general, it's really hard to give a rule because, for example, if you have a ResNet, basically many layers can just learn the identity mapping. So you can have like 1,000 layers, but in reality it behaves like a 10-layer network. So it's really hard to have a rule that will say, based on the number of layers of your backbone, this is how much projector you should use. And that's why now people are moving more to say, okay, maybe I don't have to use a projector, but then a posteriori I have to select features from many different layers. Because basically the last few layers will act as a projector, and if it's bad, I just pick features from the previous layers. So this automated way of feature selection, because as you said, it's really hard to a priori prescribe what should be your projector, or even if you need one, depending on your hyperparameter. So, because also it's not just the loss, it's also like the training set size, right? All those things. In some cases, you may not need a projector at all, but yeah, it's really hard to know a priori. So yeah, this is also something that gives a nice boost in performance. And then, yeah, so again, like all of those are open question, what to do with a transformer, how to deal with like spatial features. Do you want to aggregate them with pooling, or actually do you want to keep the spatial information? All of those things are open question and really depend on the downstream task you want to use. And that's why this is like pretty much the Wild West, right? And that's why it's really important to figure out a nice way to cross-validate because you have so many open questions that it's not clear how to do it for all architectures. That's why most of the SSL pipelines or the new SSL papers you see, they often focus on one type of architecture, let's say like VITs for vision. And in general, they will not really show, okay, I apply the exact same SSL loss and setting across VIT, ResNet, ConvNet, DenseNet, you know, all those things. Because for each of them, you will have a different recipe. So this is also something to keep in mind. Yeah, and maybe like the most important thing is when you are trying to make your SSL pipeline work, you really need to be patient because it is extremely sensitive to all those hyperparameter and designs. And also, whatever insight you think you may have gained from some loss or some architecture, maybe does not generalize at all to another architecture or another loss. So here is just a small example where we show, so it's again on ImageNet, with SimClear Barlow twins, we vary the learning rate for different batch size settings. And we look at the accuracy on ImageNet. So it's like in distribution, right? It's a really nice setting, same axes, basically, same images. And you see on SimClear, you have some trends or the performance vary as a function of the learning rate. And it's somewhat comparable with different batch size. Of course, the optimal value may vary a little bit, but the trend is roughly the same. But then if you use Barlow twins, you may have a bit more erratic performances. And again, all of those come because although the SSL losses rely on the same two core principles, if you look in terms of behavior of the gradient, some may be better behaved than the other. And this means that when you change hyperparameters, the way it will impact your final representation may vary depending on architecture and loss. It's really common, for example, that you have some SSL loss that's designed for a ResNet, and then you just switch a ResNet to a VIT, and suddenly everything collapses. So you have to really be mindful about those things, because in supervised learning, this is not so much the case, right? If you do ImageNet supervised learning, you have a ResNet 50, and suddenly you show just a ResNet 9 or a VIT huge, roughly you will still get a non-random performance, right? Maybe you will have a bit different performance, but it's not gonna go from 80% top one accuracy to just random, so 0.001 or whatever. But in SSL, this can happen a lot of times. So that's one thing you really have to keep in mind, is that basically there is no guarantees, and everything is open for questioning. So that's why this is really one of the challenges, and that's why most of the people now, either they try to develop new SSL losses when they have access to huge clusters because they can do all this cross-validation easily. And if you don't have access to many GPUs, most of the way you will interact with SSL is by using some pre-trained model and try to figure out how to fine-tune it or adapt it a bit for your case, because it's really expensive to redo everything from scratch, especially if it's a new data modality, right? Because then you also have to figure out what is a good data augmentation, what is G, maybe what is even a good architecture, because most of those architecture have been derived for computer vision. So yeah, many open questions that are gonna be between you and the state-of-the-art performance. And then, yeah, so one good resources to start with maybe is this cookbook, where we try to combine as much practitioner's guideline as possible. And the goal of this was really to be fully transparent and not hide anything under the carpet, because this was not submitted to any conference. This is just sitting on archive. And the goal is to try to give the answers on how to do cross-validation, how to pick your architecture, all of those things in the most straightforward way. So you will also see in it many cases where we explicitly state, okay, when you use this combination of ROS and architecture, you have more challenges. When you go from a ResNet to a transformer-based architecture, be careful about your optimizer, all of those sort of tricks, you will find them there. And yeah, you can just Google the name and you will find it easily on archive. Surprisingly, there is some bug now with Google Scholar. So for some reason, you cannot cite the paper anymore. No, the Google Scholar bot did not like it, but whatever, you can still find it on archive. That's all that matters. Yeah, and so just to conclude this second part. So as we saw before, basically SSL is this sort of superset of many of existing machine learning pipelines, right? Supervised learning, unsupervised learning. It all depends how you define your graph and how you define how you set up your loss. And so the strength is really in giving you much more freedom to skew the representation that you learn. So that's why also it's much less stable, because suddenly all the power is in your hand. And so this means that at the same time it's great because you can really push for performances, but at the same time you can also get something completely random. So it's something to keep in mind, right? You cannot have one without the other. And of course, the biggest challenge is how to do reliable cross-validation and how to make things work reliably out of the box, which is really not the case now. If you try to have a new dataset modality that was not used before, most likely it will just fail unless you adapt every piece of the SSL pipeline. So that's one thing to keep in mind. And also, if you really want to push for performances, it's not just about SSL, but also about all the small tricks that people have come up with through the last 5-10 years. Because once you add all those small tricks, you really have a huge difference in the final numbers that you report in like table 1 in page 1, right? So this is really something you have to keep in mind, is that if you just have basic SSL implementation and you see you are like 5-10% below the state of the art, this should not discourage you, because maybe just those tricks will be what brings you to the top one space, basically. And then the last thing I will say is that yeah, it's a really active area of research. So there is really a lot of potential. And I think even more if you move away from natural images. So basically that's perfect for you and for Earth observations. So yeah, so that's it. And yeah, if you have any questions or want to discuss, I will be here also tomorrow and Wednesday. So happy to discuss more. Thanks. So no questions, or maybe lunch questions? Yeah.
One more question.
Yes.
Does that fit sort of the invariance
Yeah.
framework?
Yes. Yeah. So you can reformulate those as well. So basically, the way you do it, so in those pretext tasks, you try, for example, to predict. So for example, there is common jigsaw puzzle where you have an image, you cut it into like 9 pieces, and you shuffle them around, and the goal is to predict, okay, how to reorder the pieces so that you get a natural image. And so basically, you can see reframe this under this viewpoint, with the data augmentation being the like jigsawing process. And then you can show that when you use this loss, which in this case would be supervised with like the ordering of the pieces, you also prevent collapse over the search space of the classes. But still, it's going to be much more collapse because you have the space of classes is going to be really small. But still, you can reframe it this way, and you can actually show in some cases why those pretext tasks are actually not strong enough, because the minimal representation you need to solve them can have really small rank, and you can still perfectly solve that pretext task. But because the rank is so small, it's not useful for many downstream tasks. So that's one of the things why pretext tasks sort of became maybe behind current SSL, that it's really hard by hand to define a pretext task that is rich enough so that the representation you learn is going to be useful for many downstream tasks. Because there can be some things, so there is also like coloring, right? Those type of things. And the problem is that just by learning really, really few features, so like a representation space of, let's say, rank 2, already it's enough to solve many of those pretext tasks, and therefore your representation is not rich enough. But yes, that's also one thing that could be a good baseline, predicting, for example, the flipping you apply to the data augmentation, thing like this. But again, the challenge is how to define a rich enough pretext task. And this is basically as hard, maybe even harder than all those other open questions that you have with those sort of joint embedding SSL methods. Because the problem also, just to finish with pretext task, is that there can be a lot of sort of silent bugs where you think you define a pretext task that is really hard, because as a human, for you, it's really hard. But actually, there can be some really simple statistics about the image, like color histograms or whatever, that are actually sufficient to solve the pretext task. So you have a lot of sort of silent solutions like this that will make your representation really ad hoc and simple, so unuseful. But you, as a human designer, you may think that, okay, it does not make sense. You should learn a strong representation. So it's also one problem with pretext task, is that between what you think is hard and what statistical learning mechanism will find, there is a big gap between those two things. Yes.
Most users Japanese guidelines cover in terms of how many resources to have. There's, you have 3 different cell backbones. How do I have those?
Yeah, good question. So basically, so there are a few ways you could do that. So one, you could try to use this sort of feature selection, like the head to toe one, to at least try to get the best features from your backbone. But then in practice, you will want to do this. So if you have access to 3 SSL backbones, you will want to do this feature selection on each of them, try to concatenate them, and use that to try to get sort of an ensemble of the 3. In practice, you will want to combine as many of the pre-trained backbone you have access to in sort of the smartest way possible. This is what is going to give you the best performance rather than try to pick only one. basically. And then there are also many other things. So for example, one thing you could do is some sort of distillation between them, or you could find other way to combine them. But in general, if what you want is just get the best final performance, you don't want to pick anything. You want to just try to give as much information to your linear classifier and then do some feature selections through regularization or whatever. But this is what will give you the best performances. So use as many pre-trained backbones as you can, find a smart way to ensemble them, and then use that to basically solve your downstream task. And in practice, this can take many forms, even like fine-tuning. If you have access to one backbone, it could be, how do you pick which layers to fine-tune? Or maybe you want to do something like LoRa, right, where you have some low-rank update of all the parameters. So again, those are all open questions. But in general, you don't want to do anything by hand. You want to give as much freedom to the linear classifier or whatever, and then you can use L1 regularization to automatically select what is best. But yeah, ensembling is usually better than just picking one backbone. Good. So I think lunchtime.